Hello everyone, this is the second lecture, it's the Gauss-Jordan elimination method. So in lecture 1, you learned about system of linear equations and you learned there are two techniques to solve for the solutions of the system of linear equations. One is called the substitution method and another one is called the elimination method. So in this lecture, we're going to learn another method to solve the solution of system of linear equations. This again calls Gauss-Jordan elimination method. And to do this, we need to use notations, matrix notations, and another one is called the augmented matrices. Even though we haven't formally defined a matrix, eventually we're going to do that in lecture 4. But for now, because we need the notation of the matrix, so we just briefly talk about matrix and how to form the augmented matrix to solve for the solutions of the system of linear equations. So let me okay, so that's the first learning objective. The second learning objective is to recognize and use elementary row operations. There's going to be 3 elementary row operations that you can perform on the augmented matrix to find equivalent linear system. And of course, at the end, we're going to have these, we're going to have some example how to solve system of linear equation using Gauss-Jordan elimination method. All right, so first let's write down the definitions of matrix. This is the informal definitions. Like I say, eventually we want to spend some time on the formal definitions for matrix. All right, so matrix is a rectangular array of numbers. Right. Written within brackets. It depends on the persons who deal with matrices. You can use brackets, you can write these numbers inside a bracket, you can write this number inside parentheses. Eventually you will see that either way should be fine. But for now, let's just focus on using brackets. Okay, and the numbers in the array are called the entries of matrix All right, so here is an example of a matrix. Usually we use capital letter to indicate a matrix. Smaller letter eventually will be used to vectors. Okay, so capital letters for matrices. Okay, now I have a matrix of the form 2, 1, -1, 1, 0, 5, -1, 3, and -2. So as you can see, this is going to be called the square matrix or rectangular array of numbers. A square array of numbers, doesn't matter, right? And you can see that this number is going to be called, so number 5, 2, 1, -1, whatever numbers inside this bracket. These are called the entries of the matrix. And there's all the definitions that you might want to know at this point, that all of this entry combined together is create something called the row of matrix. And because in the horizontal line, right, so it's called the row of matrix. All of this number combined together is called the column of matrix. So that is as much as you want to know about matrices at this point. That matrix again is the array of numbers written within brackets, and the numbers are called entries of the matrix. In the matrix, you have rows. In this case, you have three rows, so row 1, row 2, row 3, and there are 3 columns in this particular matrix. So you have 1 column, 2 column, and 3 columns. All right, so now from the system of linear equations, we're going to rewrite that and form, using the information of the linear system, form something called the augmented matrix. Okay. So consider the following system of equations. So 2x plus 1y minus 1z equal to 3, and then 1x plus 5z equal to 1. And the last equation is negative 1x plus 3y minus 2z equal to 0. Okay, so I explicitly write down 1, negative 1, 1, negative 1, so that you can see that the constant in front of the variable x, y, and z will be collected to put into a matrix. Okay, and if you notice that, so you have 2, 1, negative 1, so it's corresponding to the entries in the first row right here. 1, 0, 5 corresponding to the second row in the matrix, and negative 1, 3, negative 2 corresponding to the third row. And all of these numbers combined together or get put into the matrix, and the matrix in this case is called a coefficients matrix. So from this linear system, I have a coefficient matrix A of the form. Again, this is going to be 2, 1, negative 1, 1, 0, 5, negative 1, 3, negative 2. So I know that this is coefficients matrix. I'm not going to care too much about the x, y, z variables at this point, because the method of Gauss-Jordan eliminations method don't require you to explicitly write down x, y, and z in the matrix. So we're good for that. Now, another matrix that we want to focus on is the entries of the right-hand side. So you have 3, 1, and 0. And they put together, we have something called the constant matrix. So 3, 1, 0. So this is the constant matrix. And the form of this constant matrix is the column, is called the column matrix, because it's just written in one column. Okay. Now, how could you form the augmented matrix? So the augmented matrix is the combinations of coefficient matrix and constant matrix. So what you can do is you write like this. A matrix, the augmented matrix is of the form. The first entry here, or the first matrix, is the coefficient matrix, and then a big vertical line. And on the right-hand side of that is the constant matrix. So this is the augmented matrix that we need to form. So put everything together. You got, this is 2, 1, negative 1, 1, 0, 5, negative 1, 3, negative 2, big vertical line, and then 3, 1, 0. So we just formed the augmented matrix of the linear system given here. Okay. Now from this augmented matrix, eventually we're going to use something called the elementary row operations and perform the Gauss-Jordan elimination method to obtain the solutions of the system. Okay, so let's go through a few more definitions before we get to the example of solving the system of linear equations. Okay, the next definitions I want to mention is called the row echelon form. So a matrix is in a row echelon form if it satisfies the properties So there are two properties that help you define if a matrix is in a row echelon form or not. So the first property is that any rows of 0 are at the bottom of the matrix. And the second property is that the leading entries in any row occurs on the right of any leading entry above that. So we're gonna see an example right after this, but just let me write the definitions down first. So the leading entries in any row occur on the right of the leading entry above it. Okay, so it's a little bit unclear at this point for the second property, but let's consider the following example. So I have the matrix of the form 2, 4, 1, 0, -1, 2, 0, 0, 0. All right, so this matrix is in the row echelon form because it satisfies the first condition, which is the zero entry, or the row of zeros is at the bottom of the matrix. And it also satisfies the second definition because the leading entry, all right, so let me note here. So this is called the leading entry of row 1. Okay. And this is called the leading entry of row 2. And you can see that the leading entry of row 2 is on the right of the leading entry above it. I hope it makes sense to you. Okay. And because it satisfies these two conditions, this matrix is in the row echelon form. All right. So let's consider another example right here. So I have the matrix of the form 1, 0, 1, 0, 1, 5, 0, 0, 4. All right, so this matrix is also in the row echelon form, even though you don't have any rows of zeros in the matrix, that is fine. But the more important part is that the leading entry in any row occurs on the right of the leading entry above it, right? So we have 3 rows in this case, and you can see that in row 1, you have one leading entry, the leading entry 1. So let me note here, this is the leading entry. 1. And in the second row, the leading entry is on the right of the one above it. And in the third row, this is also the leading entry, right? And because it stays on the third row, is actually on the right of the leading entry above it. So these two examples we just have here are the matrices that are in the row echelon form. Okay. But when you do the Gauss-Jordan eliminations method, you want to actually reduce the row echelon form or the augmented matrix into the reduced row echelon form. Okay, so it's much more reduced compared to just the row echelon form. So a matrix is in a reduced row echelon form if it satisfies the following properties. All right, so you have one extra property compared to just the row echelon form. Okay, so for the reduced row echelon form, the first property is very much the same with the one in the row echelon form. That is, any rows of zeros are at the bottom of the matrix. Now, the second property is that the first non-zero element, or this in this case we call it the leading entry, in each row is 1. All right, so different, a little bit different from the row echelon form. The leading entry, right, the first non-zero element or the leading entry in each row has to be 1. Not just any number, it has to be 1, right? It cannot be 2, right? It has to be 1. So you have to somehow manipulate the matrix so that you can obtain 1 from this entry. It cannot be -1. Again, you have to somehow manipulate the matrix so that you can obtain 1 from this -1. We will see how to do it. We will learn how to do that later, right? All right, so again, the first non-zero element or the leading entry in each row is 1, or this is called the leading 1. And one more conditions here for this property is that all elements below leading 1 are zeros. Below and above the leading 1 are 0. Now, the third property is that the leading 1 in any row occurs on the right of the leading 1 above it, of the row above it. Okay, so again, let's recap the reduced row echelon form. It's very similar to row echelon form, right? Especially for the first properties that any row of 0 are at the bottom of the matrix. But the second properties require more specific details for the leading entry. That is, you need to turn the leading entry of any numbers into a 1, right? So we call that a leading 1. And all the elements below or above the leading 1 has to be equal to 0. And the leading 1 in any row occurs on the right of the leading 1 of the row above it. Okay, so let's see the following example. So let me write down instead of any matrix, let me write down an augmented matrix. So I have the augmented matrix of the form 1, 0, 0, 1, and then a vertical line, then 2, -3. Right. So even though we don't have any row of 0, that is fine. But this is still the reduced row echelon form because the leading entry here is equal to 1 in the first row. The leading entry for the second row is also equal to 1. And this one is on the right of the one above it. All right. Now this one is the in the reduced row echelon form. So there's another example that we can play around with. So this is 1, 0, 0, 1, 0, 0. Then big vertical line, 3, -1, 0. Okay. So this is the reduced row echelon form again. Now this matrix satisfies the first conditions, that is the row of 0 is at the bottom of the matrix. In the first row, you have this the leading one, and the zero, the entry below that is r equal to 0. Now on the second row, you have this is the leading one, and it stay on the right of this one. All right. And the entry above and below that are 0. So this matrix is in the reduced row echelon form. All right, so I hope this gives you some idea of how to recognize the row echelon form or the reduced row echelon form. Okay. So let me write down another definition. It's called the pivot positions, right? So we talk about the leading entry, we talk about the leading one. Together, they have the same name. It's called the pivot positions. So for the pivot positions, the entry of the matrix chosen to become a leading entry is called a pivot positions. And this phase of the process is called pivoting or pivoting process. All right. So at this point, we have enough informations, definitions to actually going to perform, to learn about elementary row operations, and later on the Gauss-Jordan eliminations. Okay, so for elementary row operations, right, the procedure to reduce any matrix to a matrix in row echelon form or reduce row echelon form for that matter require 3 elementary row operations. Right? So the following elementary row operations can be performed on a matrix. Okay, so the first operation is to interchange 2 rows. Now, if I have row I in row J, for any I in any J for that matter, the notations I'm going to write is R sub I. R stand for row. I is the number of the ith row of the matrix. And I interchange that with row J. So that is the first elementary row operations that you can perform on the matrix. The second elementary row operation is to multiply a row by a non-zero constant to create a new row. So multiply a row by a non-zero constant. Okay, so if I want to change the row I, right, I can multiply row I by a non-zero constant to create a new row I. So I multiply k by row I for k is a non-zero constant, and I get a new row, right? And the new row I for that matter. Now the last elementary row operations that I can perform is to add a constant multiple of a row to another row. So now I have two rows. Let's just talk about two rows, row I and row J. Right. Now, if I want to create a new row I, what I can do is that I'm going to multiply by a non-zero constant to row J. And I add that with row I to create a new row I. Okay, so again, there are three elementary row operations that we can perform. First one is to interchange two rows. The second one is to multiply a row by a non-zero constant to create a new row. And then add a constant multiple of a row to another row. Okay, so with these three elementary operations, I can follow through with the Gauss-Jordan eliminations method to obtain the solutions of the system of linear equations. And there are multiple steps, of course, but there are three main steps that you can focus on. The very first one is to look at the system given to you and form an augmented matrix from that particular system. All right, so form the augmented matrix of the system of linear equations. And then after that, right, now you got the augmented matrix. What you can do next is to use the elementary row operations. Operations to reduce the augmented matrix to reduce row echelon form. And if the resulting system is consistent, then you solve for the solutions, right? Again, a quick reminder for you that consistent system is the system that either has unique solutions or infinitely many solutions. And through some example, we're gonna see when the system has unique solutions, when the system have infinitely many solutions, or when the system is inconsistent or non-solution. Right, so the last step is if the resultant system. So the resultant system is the system that you obtain through the elementary row operations process. Now, if the resultant system is consistent, we solve for solutions. Okay, so that's it for the theoretical part of the lecture. Right? So now we're gonna move on to do some example. Okay, so again, what we're trying to do is we're trying to learn another way to get the solutions of the system of linear equations. And the new method that we learn is called the Gauss-Jordan elimination method. And to learn or to perform the Gauss-Jordan elimination method, you need an augmented matrix, which is formed between the coefficient matrix and the constant matrix. And of course, to perform or manipulate the augmented matrix, you need elementary row operations. So there are three elementary row operations. The first one is to interchange two rows. The second one is to multiply a non-zero constant to one row. And the third one is to add a constant multiple of one row to another row, right? And now you obtain a equivalent system or the resulting system. If the system you get is consistent, you can solve the solution looking for either unique solutions or infinitely many solutions. If the system or equivalent system you got is inconsistent, you say that the system has no solutions. All right, so let's actually do the following example using Gauss-Jordan elimination method. So I have, again, a system of two linear equations. Now, what we need to do is to form the augmented matrix. Okay, and remember again, the augmented matrix consists of two matrices. The first one is the coefficient matrix. The second one is the constant matrix. So the coefficient matrix, so let me write down the augmented matrix here. So the coefficient matrix is 2, -3. So I pick 2, -3, 3, 4. Right, so that is for the coefficient matrix. And for the constant matrix, this is the constant matrix, so 6 1/2. And I'm gonna, right, so now I have the augmented matrix. Okay, so what do we do now? We want to reduce this augmented matrix to a reduced row echelon form. So that means you need to turn this leading entry to a 1. So we need 1 here. And to get 1, very simple, right? So you divide it for every entry of this matrix by 2, or multiply row 1 by a non-zero constant, right? So in this case, I'm going to multiply every entry of row 1 by 1/2, or multiply row 1 by 1/2, and I'm going to get a new row 1. Now, so 1/2 times 2 is equal to 1. -3 times 1/2 is -3/2. And 6 times 1/2 is +3. And we didn't make any changes for row 2, so row 2 remains the same. So we got 3, 4, and 1/2. So we need one leading one here, and we make that happen. Now remember, for the reduced row echelon form, the entry below the leading one has to be equal to 0, or the entry above it has to be equal to 0. So you want 0 here. What we need is 0 here. And to obtain that, to obtain the 0, what you do is right, so I need to borrow what I have for row 1, right? So I'm gonna multiply -3. Why is -3? Because we have +3 here, and to get rid of the 3, to turn that 3 into a 0, I need the -3, right? So -3 times 1, right? 1 occurs in row 1, so that's why I do -3 times row 1 plus the second row to create a new row 2. Okay. So I just borrow row 1, right? I don't make the changes for row 1 at all. So row 1 remains the same. I just borrow it, right? I don't change the row 1. So row 1 remains the same, 1, -3/2, 3. Right. Now for row 2, I make the changes in row 2. So -3 times 1 added with 3, it's going to become 0. Now -3 times -3/2 is +9/2, plus 4 is going to be 17/2. Okay. Similarly, I have -3 times 3 is -9, plus 1/2 is going to be -17/2. Now, we have the leading one in the first row, and the entry below that is 0. So we're good with that particular case. Now for the second row, I need a leading one here. So I say that, okay, I need 1 here. Okay, so how to turn that into a 1? Very simple. You multiply by a non-zero constant 2 over 17 to obtain the leading one. So 2 over 17 times row 2 to create a new row 2. Right, so I didn't make any changes in row 1. So row 1 remains the same. Now for row 2, right, so 2 over 17 times 0 is still 0. 2 over 17 times 17 over 2 is going to be equal to 1. And 2 over 17 times negative 17 over 2 is going to be equal to negative 1. Okay. Now I have a leading one in the second row, and this leading one is stay on the right of the leading one above it, which is good. So it's almost in the reduced row echelon form. So I said almost because I still need the 0 entry here, right? The entry above the leading one. So I need a 0 here. And to get rid of the 0, sorry, to obtain the 0, sorry, to get rid of negative 3 over 2 to obtain the 0, what I do is that I'm going to borrow row 2, right? I'm going to do 3/2, positive 3/2 times row 2 added with row 1 to create a new row 1. So why positive 3/2? Because you have negative 3/2 already, right? So you need an opposite of negative 3/2, which is positive 3/2. You multiply with 1 here, add it with negative 3/2, and you create a 0 entry there. So remember, at this step, I only borrow row 2, so row 2 remains the same. So I have 0, 1, negative 1, and row 1 will change, right? The entries of row 1 will change. All right, so 3/2 times 0, which is 0 plus 1 is still 1. 3/2 times 1 added with negative 3/2 is going to be equal to 0. And 3/2 times negative 1 added times negative 1 added with 3, it's going to be equal to 3/2. All right, so this is the reduced row echelon form of the given system, right? In other words, this reduced row echelon form give you an equivalent system of the system given in this example. So I can say that this is the augmented matrix of the equivalent system or of the system. Right, so this is x1, 1x1 times 0x2 equal to 3/2. And second equation is 0x1 times 1x2 equal to negative 1. So I get this is x1 plus 0x2 equal to 3/2. 0x1 plus x2 equal to negative 1. So therefore, from this system, we can see that the solution is x1 equal to 3/2 and x2 equal to negative 1. So from this particular example, hopefully you understand the procedure. I'll give you some idea how to obtain the solutions of the linear system or the system of linear equations through the process of Gauss-Jordan elimination method. Okay, so moving on to the next example. Right, the next example, we have the following system: 2x1 minus x2 equal to 4. And the second equation is negative 6x1 plus 3x2 equal to negative 12. Now, if you notice something that between these two equations, if you divided both sides for the second equations by -3, so divided both sides of this equation by -3, you get 2x1 minus x2 equal to 4. So these two equations actually the same, right? They just got written in a different form, right? So because these two equations are the same, there are two lines staying on top of one another. Therefore, you can draw the conclusion that the system has infinitely many solutions. Okay. However, what we want to learn in this particular lecture is the Gauss-Jordan elimination method process. Okay, so let's do that. I know it's not as pleasant as we could like, but it's a good practice for us. Okay, so let's start with forming the augmented matrix of the system. So remember, the augmented matrix consists of the coefficient matrix and the constant matrix. So this is 2, -1, -6, +3, and on the right hand side of the vertical line is 4, -12. All right, so first, for the first row, I need the leading one here, so I need 1 here. So to obtain that 1, what I do is I multiply row 1 by 1/2 to create a new row 1. So I have this is 1, this is -1/2, and this is 2. I didn't make any changes in row 2, so row 2 remains the same. All right, now I have the leading one in the first row, so the entry below that has to be equal to 0, so I need the 0 here. And to basically obtain the 0 at this particular entry, what you do is I'm going to borrow row 1, and then multiply, get 6, multiply with row 1, add it with row 2 to create a new row 2. Why +6? Because you already have -6, so you have to choose the opposite number of that to get to multiply with the leading one here. So 6 times 1 added with -6 going to give you 0. So at this step, you just borrow row 1. So row 1 remains the same. So 1, -1/2, and 2. For row 2, you make some changes. So 6 times 1 added with -6 becomes 0. 6 times -1/2 added, it becomes -3, added with 3, it's give you 0. And 6 times 2 is 12, added with -12 is going to be equal to 0. Right. So you can stop right here, right? Because the last row is the row of 0, right? So there's nothing else that you can do. There's no way you can get the leading one anymore, right? So we can say that this is the augmented matrix of the following system, of the equivalent system, of the given system in this example, right? So this is the augmented matrix of the system that you have x1 minus 1/2 x2 equal to 2, right? And we're not going to write out the last row because the last row is just a bunch of 0, 0x1 plus 0x2 equal to 0, which is a true statement. So we're not going to write it down. And the system has infinitely many solutions. Right. And to represent the solution set, right? What we do is that we're going to solve for x1 in term of x2, and x2 in this case is called, has a name, it's called the free variable, is free because you can choose x2 to be any number that you like, and x1 depends on the number that you choose. All right, so to represent the solution set, we let x2 to be equal to t, where t is any real numbers. And usually the notations, a mathematical notation for t is any real number is that t in real line. So this is the real numbers. Okay, and x1 is equal to 1/2 x2 plus 2, or this is 1/2 t plus 2. Therefore, the solution of the system is x1 equal to 1/2 t plus 2 and x2 equal to t, for t is any real numbers. Okay, so we just went through two examples. One example is where you have a unique solutions, and the second example we have the infinitely many solutions. So the two systems we just went through are the consistent system. Now for the last example, in this Gauss-Jordan elimination method, we have the system of the form 2x1 plus 6x2 equal to -3, and x1 plus 3x2 equal to 2. Now, again, if you notice this particular system, if you divide both sides of the first equation by 2, what do you get? You get x1 plus 3x2 equal to -1. So you, on one equations, you have x1 plus 3x2 equal to -1. And the second equation is x1 plus 3x2 equal to 2. So obviously, this system is inconsistent, right? Because x1 plus 3x2 cannot equal to this two different values, right? So the system is inconsistent. We know for sure that there's no solutions because these two lines are parallel. But again, the procedure we want to learn is the Gauss-Jordan eliminations method. So let's see what happened. So again, the first step is to form the augmented matrix of this particular system. So 2, 6, -3, 1, 3, 2. All right. So this is a good system to look at because what we recognize again that we need one here. From the last two example, what we usually do is to divide the both sides for 2. But here in this case, what you can do to make one appear in that leading entry is to swap two rows. So I'm going to swap row 1 and row 2. And now row 2 become row 1 and row 1 become row 2. So row 1 now has the entry of 1, 3, 2. The second row now have entries of 2, 6, -3. Okay. Okay, good. You have the leading one in the first row. That means the entry below that has to be equal to 0. So we need this 0 here. And this is a +2. So when you manipulate the matrix to get, or the rows to get the 0, you need the -2. Right, so we want to borrow to row 1. So -2 times row 1 plus row 2 to create a new row 2. So the augmented matrix becomes, again, you just borrow row 1. You didn't make any changes for row 1. So you do have the same entry in row 1. So 1, 3, 2. Now for row 2, what you got is -2 times 1 added with 2 becomes 0. -2 times 3 added with 6 is going to be 0 again, because -2 times 3 is -6, added with 6 will be 0. And for this entry, what you have is -2 times 2 is -4, added with -3, it's become so it's big, sorry. So it's become 7, -7. Okay, so we're going to stop right here because we have a false statement in the second row, because this row, right, 0x1 plus 0x2 equal to -7, which is a false statement. So this is the augmented matrix of the system. X1 plus 3x2 equal to 2, and 0x1 plus 0x2 equal to -7. This is the false statement. So therefore, you say that the system has no solutions. The system is inconsistent, and thus has no solutions. Okay. And through these 3 examples, hopefully you get an idea how to perform Gauss-Jordan eliminations method to obtain the system of linear equations. Again, the procedure for Gauss-Jordan elimination method is to first form the augmented matrix, and then use elementary row operations to reduce the augmented matrix to a reduced row echelon form. And then if the system is consistent, then you solve for the solutions. If not, you say that the system has no solutions. All right. So moving on to a few more definitions. Now, the next definitions we're going to look at is called the homogeneous linear systems. All right. So a system of linear equations is said to be homogeneous if it can be written as AX equal to 0. So let me stop right here, right? So for A is a matrix, this is the coefficient matrix. So the X with the arrow on top of that, we call that a vector or a column matrix, right? So A times X, usually X is indicated or used for the column of variables. So X1, X2, X3, so on and so forth, or X, Y, and Z, so on and so forth. And equal to a right-hand side, this is the constant vector that we talked about that earlier. But the constant vector now is just a bunch of zeros, okay? So if you have a system of linear equations, and that linear equations can be written in this form, AX equal to 0 vector, then you say that the system is homogeneous, where A is an M by N matrix. So this m by n is called the side of the matrix. Again, we haven't formally defined a matrix, a side matrix for that matter. It's just that we need the definitions to talk about the homogeneous linear system. Okay, so bear with me here. Eventually, like I say, eventually we're going to talk about matrices in more details in lecture 4. All right, so this is the side of the matrix. And 0 with this notation with the arrow on top is the 0 vector. And is in Rm. So this is called the dimensions of the vector. This is m dimensional, right? If you have R2, that means the vector is 2-dimensional, 2 entries. If 0 is in R3, then that is 3-dimensional. There are 3 entries. So in this case, you have Rm, that means this is m-dimensional, and you have m entries of the zeros. So 2 remarks here. Ax equal to 0, right? So there's a lot of new things, new knowledge that we haven't talked about that much yet, but we just need the information that Ax equal to 0 form a homogeneous linear system. Okay, so this homogeneous linear system always has at least one solution, and that solution is x equal to 0, right? So vector x is equal to vector 0, and this type of solution is called the trivial solutions. And other than that, otherwise, Ax equal to 0 has non-trivial solutions. Or non-zero vector x. Okay. All right, so that Ax equal to 0, homogeneous linear system, always consistent, right? Because it always has at least one solutions. Okay, so now moving on to the next definitions, which is called the free variable. A free variable of a system of linear equations is a variable where you can choose any value for the variable. And you see the free variable occur in one of the example earlier. So we see that in this example 5, the free variable occur in this equations, right? So in this case, x1 minus 1/2 x2 equal to 2, and we choose that x2 to be a free variable. Of course, there's another case that you can work with, that you can choose x1 as the free variable, right? So again, the free variable is the variable where you can choose any value for that particular variable. Okay, one more theorem, one more example, and we're good to go. All right, so the next theorem is that every homogeneous system of linear equations is consistent. Right. Moreover, if the system has fewer equations than variables, then it must have infinitely many solutions. Okay, and we'll see this particular theorem in the following example. So we consider the following system of linear equations. Rather, this is the homogeneous system of linear equations because the right-hand side is equal to 0. Now we're going to use the Gauss-Jordan elimination method on the augmented matrix. Right? So we need the augmented matrix first. So the coefficient matrix include 1, -1, 3, 2, 1, 3, and the constant matrix is 0, 0. All right, so it's lucky for us for this particular augmented matrix, you already have the leading one. So therefore you need to turn this entry into a 0. So we need the 0 here. And to obtain 0, what we do is we're going to borrow the entry in row 1. So -2 times row 1 plus row 2 to create a new row 2. So we just borrow row 1 without making any changes. So row 1 remains the same. Now row 2 becomes, so -2 times 1 added with 2 becomes 0. -2 times -1 is +2 times plus 1 become +3. Then -2 times 3 is -6, added with 3 is -3. And -2 times 0 is 0, added with 0 is still 0. Okay. So we have the leading one in row 1 already, so it's good. In row 2, we need to make this 1, right? So need 1 here to turn that into a leading one instead of the leading entry only. So we'll need 1 here. So to obtain 1, we're going to multiply row 2 by 1/3 to get the new row 2. Again, we didn't make any changes in row 1, so row 1 remains the same. So this is 1, -1, and 3, 0. And this is 0. So the next, for this entry, 3 times 1/3 is 1. And -3 times 1/3 is -1 equal to 0. Now you have the leading one in the second row, which is good. Now you want to turn this into a 0. So we need the 0 here. So to get 0, what we're going to do is we're going to borrow row 2. Right, so this is -1, so the opposite of that is just +1. So row 1 times row 2 added with row 1 to create a new row 1. We just borrow row 2. There's nothing changes in row 2, so row 2 remains the same. So 1, 0, 1, -1. And this is 0. Right. So for row 1, you get 1 times 0 is 0 plus 1 is still 1. 1 times 1 is +1 times added with -1 becomes 0. +1 times -1 is -1, added with 3 is +2. And this is still 0. Okay. So we can stop right here because there's nothing else that you can do. You have the leading one in the first row, and the entry below that is 0. We're good. Now for the second row, you have the leading one, and the entry below above that is 0. So there's nothing else we can do. So we say that this is the augmented matrix. of the system x1 plus 3x, plus 2x3 equal to 0, and x2 minus x3 equal to 0. And you can actually solve from first equations. You solve for x1 in terms of x3, and you solve for x2 in terms of x3 as well. So we get x1 equal to -2x3, and x2 is equal to x3. Right. And we choose x3 to be a free variable in this case. So you let x3 equal to t for t is any real number. And so this is the fancy R. Right. Then you get that x1 is equal to -2t, x2 is equal to +t, and x3 is equal to t as well, for t is any real number. And that is the solutions of the system, of this particular homogeneous system. And there are infinitely many solutions because t is all real numbers, and all real numbers is just infinitely many numbers, right? So there are infinitely many solutions. Okay. And for this example is also show that if the system has fewer equations than variables, then it must have infinitely many solutions. So you can see that there are 3 variables, x1, x2, x3, right? But there are only 2 equations, so therefore you automatically can say that there's infinitely many solutions. And this is how we obtain the solution set for the infinitely many solutions case. So that's it for me for this lecture. Please let me know if you have any questions. Thank you.